Hello again, another Agakala React, and today we will be watching From Today to the Year 4000, Future of Space Travel and Spacecraft. And if you're watching my videos, you know that I do like science fiction, so this is insane curiosity, so let's just jump into it and see about that. What is there to say? Because it is science fiction kind of. So, yeah, there you go.
Future of Space Travel. Time-lapse of spacecraft advancements 2025 to 4000. The great scientist Carl Sagan once said that, in the long run, every planetary civilization will be endangered by impacts from space. Therefore, every surviving civilization is obliged to become spacefaring. So if the destiny of humanity lies in conquering space, we must carefully consider the spaceships of the future that will get us there. Join us as we unravel the mysteries and possibilities of future spacecraft, taking you on a voyage through the corridors of the cosmos from the near future to the year 4000. (2025) SpaceX, in collaboration with NASA and Blue Origin, launches the first next-generation electric ion engines. These engines work by ionizing gas, like xenon, creating positively charged ions which are accelerated by an electric field inside the engine and expelled at high speeds, generating thrust. The process is highly efficient but provides low thrust, making it suitable for long-duration space missions, facilitating the reduction of travel times between celestial bodies. Reusable rocket technology becomes the norm rather than the exception. SpaceX's Falcon 9 and Falcon Heavy lead the charge, with routine launches and landings drastically reducing the cost of access to space and establishing a robust ecosystem for low Earth orbit (LEO) and beyond. 2029. Reusable vehicles equipped with state-of-the-art heat shield technologies are developed. These spacecraft feature robust thermal protection systems capable of withstanding the extreme temperatures encountered during re-entry into Earth's atmosphere. With the Artemis program in full swing, the Moon emerges as a focal point for human exploration, and we herald the establishment of permanent lunar habitats led by NASA in collaboration with Blue Origin and other international partners. These companies establish lunar outposts that not only help us to mine lunar resources such as water ice and rare minerals, but serve as bases for scientific research, manufacturing, and refueling stations for further space exploration missions. 2030. NASA initiates the deployment of fundamental components for an orbiting fuel station, facilitating spacecraft refueling and maintenance directly in Earth's orbit, eliminating...
I'm just kind of curious because I know this is only from last year and we are in 2025 and they're talking about 2030, so that's 5 years ahead. But is that actually the plans that NASA have out? Because I know NASA works like in decades long projects, so like...
necessity for spacecraft to return to the surface. This enables extended mission durations, reduced reliance on Earth's resources, and increased operational flexibility for spacecraft operating in space, fostering a sustainable and economically viable space ecosystem. 2032. The cosmos becomes a construction site as in-orbit assembly techniques, which are methods for constructing structures such as space stations or habitats directly in space, revolutionize the development of large-scale space stations and habitats. This leads to the construction of modular structures that can be assembled piece by piece in space, lowering the logistical difficulties involved in launching pre-built structures and opening the door to the development of expensive habitats that can support human habitation for lengthy periods of time. These customizable configurations also allow for spacecraft to be tailored precisely to the unique requirements of each mission and payload. By employing standardized interfaces and interchangeable modules, spacecraft designers can rapidly assemble and reconfigure vessels to meet evolving scientific, commercial, and exploration objectives. 2033. Deployment of swarms of microsatellites for detailed mapping and monitoring of celestial bodies, enabling precise navigation and resource identification for future missions. These advanced microsatellites are equipped with cutting-edge sensors and imaging systems capable of capturing high-resolution data, facilitating precise navigation and comprehensive resource identification for forthcoming missions. Leveraging sophisticated onboard processing capabilities, These microsatellite swarms autonomously analyze data in real time, enabling rapid decision-making and enhancing mission efficiency. 2034. The initial testing of small-scale nuclear fusion propulsion systems. Tri-Alpha Energy and General Fusion collaborate with space agencies to develop compact fusion reactors capable of producing abundant, clean energy for spacecraft propulsion systems. These systems work by fusing light atomic nuclei to release vast amounts of energy, generating thrust on an unprecedented scale. These propulsion systems not only have reduced interplanetary transit times, but also increased payload capabilities and extended mission durations. These systems rely on isotopes of hydrogen, abundant in resources throughout the universe, as fuel sources and are therefore more sustainable. 2035. Mars colonization efforts intensify. During the perihelic opposition, when Mars is closest to the Earth in its orbit, SpaceX's Starship, equipped with advanced life support systems and radiation shielding, begins transporting settlers to Mars. Collaborative efforts between space agencies and private companies lead to the construction of Mars habitats using on-site resources that significantly reduce the cost and logistical challenges of colonization. Asteroid mining emerges as a viable and economically feasible industry, leveraging in situ resource utilization (ISRU) techniques. Spacefaring companies begin to deploy robotic spacecraft to near-Earth asteroids rich in precious metals and rare minerals. Advanced autonomous mining techniques are employed to extract resources, which are then transported back to Earth or used for in-space manufacturing. Hey guys, we did a video about the time-lapse of the first 10,000 days of Mars colonization. Be sure to check it out. 2040.
Ethan. Yeah, 2040. That's 15 years away, but still. That's kind of something that so far I'm really kind of curious if this is based on some like actual space agencies plans out there, or is it more about just literally just science fiction now? Yeah, I'll be back in a second. Okay, I'm back, and let's just jump into it and see what's going on then. It's 2040, 15 years away from now. Might still be alright, hopefully.
The first interstellar probes, propelled by fusion-powered engines. These probes, equipped with advanced sensors and communication systems, set out to explore nearby star systems and their exoplanets. Breakthrough initiatives like Breakthrough Starshot aim to send nanocrafts to Alpha Centauri at a fraction of the speed of light. 2042. With the deployment of autonomous spacecraft and maintenance drones, the cosmos becomes a self-sustaining ecosystem. Emerging from a collaboration between Northrop Grumman and the European Space Agency, these robotic assistants perform intricate repairs and inspections on orbiting spacecraft and infrastructure. They come equipped with advanced tools and guided by sophisticated AI algorithms, which enable them to conduct precise operations in the unforgiving environment of space and ensure the continued functionality and safety of critical space assets. 2045. Artificial intelligence takes center stage aboard spacecraft, completely revolutionizing navigation and control systems with unprecedented levels of autonomy, decision-making capabilities, and capacity to adapt to the rigors of long-duration missions across the solar system. The integration of AI algorithms into spacecraft avionics enhances reliability, safety, and autonomy in space missions. It also enables fault detection, autonomous navigation, adaptive control, predictive maintenance, and risk assessment, effectively reducing reliance on ground controls. 2046. Nanotechnology is integrated into spacecraft maintenance and repair at the molecular level. Nanobots equipped with advanced sensors and tools navigate spacecraft surfaces, identifying and repairing structural damages with unparalleled precision. These nanobots operate autonomously, executing intricate repair tasks without the need for human intervention, effectively eliminating the need for expensive and risky maintenance missions. Swarm intelligence algorithms for autonomous spacecraft coordination and collaboration are deployed, enabling complex missions with distributed decision-making capabilities. This is followed by the deployment of gravitational wave propulsion systems for efficient and low-energy interstellar travel, as well as the integration of virtual reality and telepresence technologies for immersive exploration and remote operation of robotic probes and rovers across planetary surfaces. 2047. Development of adaptive spacecraft skins capable of dynamically adjusting thermal properties and surface characteristics in response to changing environmental conditions. These skins incorporate smart materials and microfluidic channels that regulate heat exchange and surface morphology. As temperatures fluctuate or encounter varying levels of radiation, these skins automatically adjust, optimizing thermal insulation or dissipation and altering surface properties for enhanced protection or maneuverability. With such adaptive capabilities, optimal performance and durability of spacecraft across diverse mission profiles, from orbiting in extreme heat to traversing icy celestial bodies, is ensured. 2048. Self-healing materials and cutting-edge 3D printing technologies are integrated into spacecraft systems to enable in-situ repairs and component replacement. The former consists of materials that are designed to autonomously mend structural damages caused by micrometeoroid impacts and wear over time, while the latter allows for the on-demand fabrication of spare parts and intricate components directly aboard the spacecraft. 2049. Life support systems employing closed-loop recycling technologies are introduced alongside advanced synthetic biology techniques for onboard food production and recycling. These cutting-edge systems minimize the need for resupply missions by efficiently recycling air, water, and waste within confined spacecraft environments, achieving a synergistic integration of biological and mechanical processes that create regenerative ecosystems capable of supporting extended crew missions to distant celestial bodies. Quantum communication networks utilizing entangled photon pairs for secure information transfer safeguard space-based assets against cyber threats and interference. 2051. The pressing necessity for robust asteroid defense mechanisms become increasingly evident amidst the establishment of colonies on Earth, the Moon, and Mars. Innovative trials are currently underway, centering on the implementation of propulsion systems directly onto asteroids to facilitate controlled alterations in their trajectories. These groundbreaking initiatives signify a pivotal stride forward in fortifying our extraterrestrial settlements against the looming threat of catastrophic asteroid impacts, safeguarding the future of humanity's expansion into the cosmos. 2053. Spacecraft design incorporates gravitational manipulation technologies to mitigate the negative psychological consequences of extended weightlessness on crew members' health. Spacecraft can replicate gravity by integrating sophisticated gravitational field manipulation devices, which lowers the dangers involved in long-term space missions.
Space station.
Spacecraft are designed with rotating habitats where artificial gravity is produced by the centrifugal forces of rotation. These rotating habitats use centrifugal force to simulate the effects of gravity by revolving around a central axis in the form of concentric rings or modules. Gravitational manipulation devices are used by spacecraft to create localized gravitational fields within designated zones, which enables crew members to exercise and carry out duties in surroundings with different gravity levels. For crewed missions to distant exoplanets, hibernation and suspended animation technologies are developed to reduce metabolic demands. 2055. The advent of antimatter propulsion in interstellar ramjets. Antimatter propulsion harnesses matter-antimatter reactions for unparalleled thrust, enabling spacecraft to achieve significant fractions of the speed of light. Meanwhile, interstellar ramjets utilize magnetic fields to compress interstellar hydrogen as a propellant, propelling spacecraft to relativistic speeds and offering the tantalizing prospect of reaching distant stars within human lifetimes. 26.
No, did I?
I've come to terms with the fact that you don't.
Oh! Sorry, I'm just a bit surprised. There's a trailer for Nobody too. I'm supposed to watch the Nobody, but they never did. So, what do I have to say about the video we're watching now? So far, the art and stuff like that is pretty cool, but in general, the rest, It's just like pure science fiction, isn't it? Because honestly, at this stage, we can. I know we just like 25 years away from the timeline that they in, but I don't know how we're supposed to get into the fact that we're gonna go to 4,000. So yeah, I'll be back in a moment. We're gonna watch that Nobody 2 trailer. Okay, I'm back, and let's jump into it. All that science fiction thing about all future of space travel and spacecraft.
2065. Advanced radiation shielding materials and technologies are developed to protect spacecraft and crew from the hazards of deep space travel during long-duration missions beyond Earth's magnetosphere. Collaborative efforts between aerospace engineers, material scientists, and medical experts yield robust shielding solutions capable of deflecting and absorbing cosmic radiation with unprecedented
that'll have to
efficiency.
come into play at some stage.
Innovative materials such as graphene-based composites and metamaterials are utilized as spacecraft designers seek ways to fortify vessel hulls against the relentless onslaught of cosmic rays, further ensuring the safety and well-being of crew members throughout extended voyages. 2071. The establishment of space-based manufacturing facilities transforms the production of materials and spacecraft components in orbit, turning the universe into a veritable industrial furnace. These orbital factories, driven by innovative firms, use in situ resource utilization (ISRU) and advanced additive manufacturing processes to produce materials and complex structures with unmatched accuracy and productivity. Space-based manufacturing facilities significantly lower launch costs and logistical complexity, while simultaneously enhancing mission flexibility and scalability by removing the limitations imposed by Earth's gravity and atmosphere. 2075. The emergence of biometric designs, which draw inspiration from nature, brings about a fundamental change in spaceship engineering. These cutting-edge spaceship concepts maximize performance in harsh settings like vacuum and microgravity by taking inspiration from the adaptability and efficiency seen in biological creatures. Spacecraft can achieve increased structural integrity, simplified energy consumption, and superior aerodynamic profiles by mimicking the solutions found in nature. Biomimetic materials, which imitate the characteristics of natural materials, help spacecraft remain durable and adaptable in a hostile cosmic environment. 2080. The dream of rapid interstellar travel becomes a reality with the integration of advanced propulsion systems, including warp drives and wormhole generators into spacecraft designs. Inspired by the theoretical frameworks of Alcubierre and Thorne, visionary researchers and engineers embark on a quest to harness the fabric of spacetime itself, bending it to their will in pursuit of cosmic exploration and colonization. Through innovative applications of exotic matter and energy, spacecraft equipped with warp drives and wormhole generators traverse the vast distances between stars in mere fractions of the time previously thought impossible, opening up a universe of possibilities for humanity's expansion into the cosmos. As the cosmic horizon beckons with newfound allure, humanity stands on the threshold of a new age of interstellar adventure, propelled by the boundless potential of advanced propulsion technologies.
Not that! Come on! Yeah, what can I add? Nothing really, because there's not much to add. So, so far it's really pretty interesting, but I really don't know what to say about it. It's all pure science fiction at this stage. Obviously something's gonna have to come if we really think about actually conquering space. We're gonna have to think about doing like those whole shielding and from the radiation and things like that, because that's gonna be needed like very badly. So yeah, that's pretty much all what I have to say. So what we have here? Okay, I'll see you in a moment. Alright, I'm back and let's just jump into it, because we have only like 4 minutes left. So, shouldn't take that long, unless it's gonna be another ad.
2091. Advanced propulsion
He did say 4,000, and we are 2491, so what the heck is going on?
systems such as wormhole generators and warp motors are incorporated into spaceship architecture to enable fast interstellar travel. Motivated by novel theoretical frameworks developed by Alcubierre and Thorne, Scientists and engineers set out to harness space-time itself and bend it to their will. Wormholes, which are hypothetical tunnels through space-time that connect distant points in the universe, are used to traverse vast distances in space almost instantaneously, effectively bypassing the limitations of propulsion methods. Warp drives compress space-time in front of a spacecraft while expanding it behind, and by doing so, it effectively creates a warp bubble that would allow the spacecraft to ride a wave of warped space-time. Within the warp bubble, the spacecraft itself would not be moving at speeds faster than light, but instead it would be carried along the expansion of space-time, allowing for FTL travel without violating Einstein's theory of relativity. Spacecraft fitted with warp drives and wormhole generators travel the vast distances between stars in a fraction of the time previously believed possible. 3100. With the development of fleets of self-replicating spaceships designed to proliferate independently and adjust to the difficulties of interstellar travel, the furthest reaches of the universe are within humanity's grasp. These self-replicating probes, equipped with highly advanced artificial intelligence and utilizing state-of-the-art nanotechnology, embark on autonomous exploration and colonization missions to far-off star systems. Each spaceship in the fleet is capable of replicating itself using raw materials found in space. The artificial intelligence systems on board these probes continuously adapt and optimize their navigation, propulsion, and resource utilization strategies, while the nanotechnology employed allows for precise manipulation of matter at the molecular level, facilitating efficient construction, repair, and adaptation of space components while en route to distant destinations. 3600. Quantum propulsion system developments further transform interstellar travel. These systems harness the principles of quantum entanglement, superposition, and tunneling for instantaneous propulsion. Quantum entanglement works by linking the states of particles regardless of distance, enabling instantaneous communication and propulsion across vast distances. This phenomena allows spacecraft to bypass the constraints of traditional propulsion methods, reliant on relativistic travel. Meanwhile, quantum tunneling exploits the ability of particles to penetrate energy barriers, facilitating rapid transit between distant star systems by navigating through space-time barriers. With quantum-enabled spacecraft networks spanning the galaxy, humanity is on the verge of colonizing the entire universe. 4000. Humanity has achieved the capability to explore parallel universes and alternate dimensions, facilitated by propulsion systems capable of manipulating space-time.
Radical!
Quantum sensors for detecting sunnable phenomena across universes, hyperdimensional navigation systems for mapping higher dimensional spaces, and interdimensional communication technologies based on quantum entanglement. This represents the culmination of humanity's deep understanding of reality and the development of sophisticated spacefaring capabilities. What technological advancement are you most excited about for humanity's future in space? Do you have any predictions of your own regarding our destiny in space? Feel free to leave your answers in the comments below.
Okay, that was I have to say that was rather strange. So I'm not sure what to think about it, and I'm not sure what to say about it. It was just kind of a strange thing. But then I shouldn't really expect much from it because it's like year 4000. We are in 2025, so that's a lot of time to go on. And obviously we can't even predict what's gonna happen in next week, so you know. Yeah, thank you very much for watching and I see you tomorrow. Bye.